Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm going to deal with the topic computational aerodynamics. And here today we'll discuss classification of PD. So before that, let's recap what we have seen in the CFD. So we have seen the different approaches of the fluid flow. So one is the control volume, which is fixed in space, and the control volume, which is moving with the flow. So these two are the basically used for the integral form of governing equations. So here the control volume, the meaning of control volume is nothing but it is an entity where we will see the change of physics of the fluid. Okay, so this control volume can be moving or it is fixed in space. Okay, so if you take control volume which is fixed in space, and if we derive the governing equations, the corresponding governing equations obtained are called like conservative form of governing equations. If this control volume is moving with the flow, then the equations when we derive, so the corresponding equations obtained is called non-conservative form of governing equations. So the difference is like here, like the mass so here the volume or the shape of the control volume is not changing. Why? Because it is fixed in space. So here mass will change actually. So this mass can control volume mass can change, CV can change, but here the CV mass is fixed actually. Okay, so the control volume which is moving with the flow, the mass will be fixed here. So here for the second case, so mass is equal to density into volume. So mass is constant for the control volume which is moving with the flow. So here how it is making constant. So basically either you increase the density or decrease the volume. So it is nothing but shrinking the control volume. So this is the scenario. The other scenario is so decrease the density and increase the volume. So the control volume will expand. Okay. So basically what is happening? So when the control volume is moving with the flow, so the mass is fixed. So why? Because the same number of fluid particles will be present always in the control volume, and the density and the volume changes every time. Okay. So this is what we have. So when we see other approach, which is the fluid element approach. So in this fluid element approach, so what we have, so basically we are deriving the governing equations in differential form. Okay, so we are deriving the governing equations in differential form, and what is happening is like, so here the molecules change. So we will be taking the Avogadro number. So there will be some these many number of molecules. So when we derive the particular fluid element, so we will derive in differential form of governing equation, and here this is conservative form and this is non-conservative form. So if you compare the difference of A and B, so A is nothing but control volume approach, so B is nothing but 10 per decimal fluid element approach. So in these approaches, what we have, so we are deriving here integral form of governing equations. Here we are deriving differential form of equations. Okay. So in general, if you see, so basically what we derive, let's say you have this integral form, let's say dou t, so rho dv, so next plus integral, so del dot rho v dv is equal to 0. So this is the integral form of governing equation. So this is which we generate for the control volume approach. So then after, so we have, so this is the direct differential form of equation, so which we develop for a infinitesimal fluid development approach. Okay, so this is the difference what we observe for the two different approaches. So here you can see basically it's a substantial derivative. So substantial derivative is nothing but, so we'll see here. So basically when a fluid element is going from one point to other point, so you need to track what is the position and what is the velocity at each and every point. So what we had done is like we had taken a Taylor series of expansion. So we know the Taylor series of expansion. If we want to know the density value at the second point. So what we do is like, so rho 2 is equal to rho 1 plus, so dou rho 1 by dou x into x2 minus x1 plus dou rho by dou y into y2 minus y1 plus dou rho by dou z into z2 minus z1. So these are the spatial derivative term plus, so dou rho by dou t into t2 minus t1. So this is what we have. So we take left side this one. So this will become minus and this will become equal to, so minus and is equal to, and we divide every term by t2 by t1. So we divide t2 by t1. So here this is getting cancelled. So here you can see limit t2 tends to t1. So this x2 minus x1 will give rise to velocity, and here y2 minus y1 by t2 by t1 will give rise to v velocity, and z2 minus z1 divided by t2 minus t1 will give rise to w velocity. So if we see in summary what we have here, so when we change so these things to these things, so here you can see, so rho 2 by rho 1, rho 2 minus rho 1 divided by t2 minus t1 will give you a total derivative which is d rho by dt. So finally, so we have this equation, so which is nothing but, so dou rho by dou t, u into dou rho by dou x, v into dou rho by dou y, w into dou rho by dou z, and you have other term which is dou rho by dou t. So this is what we have, dou rho by dou t. Fine. So now what we are writing, so we are writing the general form of equation now. So this is dou rho by dou t. So what we are writing substantial derivatives. So dou rho by dou t is equal to, so the local derivative, so d by dt is nothing but total derivative. So this dou rho by dou t plus u into dou by dou x plus v into dou by dou y plus w into dou by dou z. So this is what we have. So this term is called the local derivative term. This term is called the convective derivative term. Okay. So if you take velocity vector, so v is equal to u of I cap plus small v of j cap plus w of k cap. So the gradient, what is the formula of gradient we have? Gradient is equal to dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. So if you do dot product of these two, so then we can rearrange this equation. What is that? So dou by dou t plus v dot del. So we have written in vector form here. So this is what we have. So this substantial derivative can be applied for any terminology. Let's say, so here we are interested to find the value of density. So from one point to other point when it is changing. So in the sense, the value of density at second point. So if you want to find, so with respect to substantial derivative, you can find what is the change that is happening to the density of fluid particle at a particular time. So which is nothing but local derivative. So the convective derivative is nothing but due to the motion of the fluid, so how the density is changing. So this thing will be studied here. Okay. So with these aspects, so we will see what is the classification of PDE. So basically partial, so the meaning of the difference between partial differential equation and the exact differential equation. So here the difference, like let's say you are using dou by dou x and we have d by dx. So basically the difference between dou by dou x and d by dx is, so we have dependent variable, we have independent variables. So here for our fluids, so the dependent variables are like pressure, temperature, u velocity, v velocity, w velocity, okay, density. So these are the dependent variables what we have in our computational dynamics or in the aerodynamics or fluid dynamics. Okay, basic. So these are called dependent variables, and independent variables are like x, y, z. So these x, y, z are called the spatial derivative terms. Okay, spatial, and time is nothing but temporal. So this is called spatial and this is called temporal. So this x, y, z and t time. So basically these are called independent variables. So in our course, so our primitive basic variables what we have is like pressure, temperature, velocity, u velocity, v velocity, w velocity. So which is nothing but x direction velocity, y direction velocity and z direction velocity. We have density. Okay. So and now we have the independent variables which is x, y, z and other independent variable which is time. Okay. So based on these things, so if this independent variable or the dependent variable, let's say, so pressure is depending upon more than one independent variable. Let's say, so pressure is function of x, y and t. So the variation of pressure is happening along x direction, along y direction and with respect to time. So then we will use the partial differential equations. Why? Because so you need to see the changes with respect to three independent variables. So then we use partial differential equation. So when we use exact differential, so when let's say the pressure is function of only y, let's say. Okay, so in this case we will be using the exact differential equation. So this is the basic difference between the partial derivatives and the exact derivatives. Okay, so here in the CFD the basic important thing is, so how do you classify the partial differential equations, and this will actually depend upon the physics of the flow, so and directly will depend upon the Mach number actually. Okay, so we'll see these aspects. Now, so the basic thing what we have is like classification of partial differential equation. So our governing equations, continuity, momentum, energy, so those are written in partial differential form. So let's say we have dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0. So basically this is the full form of continuity equation. So here you can see you have dou by dou t and you have dou by dou x, you have dou by dou y, so dou by dou z. So basically these are partial derivatives. So here the density is function of time, space. Okay, so x, y, z and time. So here u velocity, v velocity, w velocity. So these are function of what is the space and x. So that's why we are using the partial derivative equations. So basically there are two techniques. So you have Cramer's rule and you have eigenvalue method. So based on these two methods, we will be using to classify the partial differential equations. Okay. So if you take the partial equations, so these are like basically four types. Okay, here you can see. So hyperbolic equation, parabolic equations, elliptic equations, and the mixed type equations. Okay, so here you can see basically the hyperbolic equations are used for the supersonic cases, and even the parabolic equations are used here for the transient or let's say near the supersonic cases we'll be using, or the low subsonic cases. Basically these two are function of time actually. So these are like initially marching problems, so time dependent problems. Then you have elliptic equations, so which is called the boundary value problem. So you have mixed types. So basically combination of parabolic and elliptic. So basically we say that parabolic in space and elliptic in time. So these combinations you have. So the thing is that, so once we have a governing equation, so the governing equation has to be decided. So this is which form. So whether it is an elliptic form, whether it is a parabolic form, whether it is hyperbolic form. So once we decide that, so we will choose what type of boundary conditions we use. So why? Because see, depending upon the type of equation we have, so the boundary conditions will vary. Okay, so the boundary conditions and initial conditions. So let's say it will be different actually. So why? Because so let's say for supersonic cases you have different sets of boundary condition, and for subsonic cases and or let's say for subsonic or low subsonic cases, you have different sets of boundary condition. Okay, so based on these aspects, so we will classify the equations, and we will actually get the solution. Okay, so why we need these things actually? So we require this thing because, so based on these equations, so from mathematics you might have learned. So let's say you will have two characteristics curve, one curve. So basically these things will tell you so how the solution is propagating with respect to time, and whether this solution let's say a point of some, let's say this is the two curves which are for the parabolic, so solution curves. So whether if you disturb this point, whether the solution is disturbed at this point or not. So let's say this is the flow that is happening. So if you disturb this one, whether it is he disturbed here or whether you disturb here, so whether it is disturbing here or here, so how the flow is propagating with respect to time and space, and these disturbances has to be studied actually. Okay, so this is the need of classification of PDE. Okay, fine. So here let's take a small a quasi-linear PDE. So here you can see there are four equations: 1, 2, 3, and 4. Okay, so basic thing what we have is like a1 dou u by dou x, b1 dou u by dou y, c1 dou u by dou x, d1 dou u by dou y is equal to f1. So basically if you see these equations, you can see that these are function of the independent variables x and y. Okay, so this is first equation. The second equation what we have is like a2 dou u by dou x plus b2 dou u by dou y plus c2 dou u by dou x plus d2 dou u by dou y is equal to f2. So this f1, f2 is like, let's say we call it as source term actually. Okay, so this can be said as source term. So here, so what is happening? So the u is one primary variable, or the let's say dependent variable. So velocity, v velocity is nothing but x, y velocity is another dependent variable. So which is function of both x and y. So v is also function of both x and y. So that is why you can see this equation. So this u is getting different, like differentiated. You have a partial differentiation with respect to x, and you have partial differentiation here with respect to y. Okay, for u. So similarly for v, you have partial differentiation with respect to x and partial differentiation with respect to y. Okay, so a1 dou u by dou x, a b1 dou u by dou y. So these two corresponds to the u velocity, and these two corresponds to the v velocity, and f1 is the source term. So this coefficient matrix is the important thing what we need to have. So here the similar thing, but the second equation, so the coefficients like a2, b2, c2, and d2. Okay, so these two are like quasi-linear partial differential equations, and basically quasi, like in the highest derivative terms it is linear, so that is what we have. So if a2 is something like u, so if you replace the a2 as u, so then it is a non-linear actually. Okay, non-linear PDE. So now here you can see what the third equation and fourth equation is. So if we have the exact differential du, okay, this can be split into partial differential form. Why? Because this u is function of both x and y. So therefore we can write this exact differential. It is like splitting the exact differential into two partial differentials. So what we have? So dou u by dou x into dx. So this is the first this thing. So u, how it is changing with respect to x, plus next u, how it is changing with respect to y. So dou u by dou y into dy. Similarly, what we have? So we have velocity. So exact differential for v velocity. So dv is nothing but, so you have dou v by dou x into dx. Okay, so this is the variation of v velocity with respect to x, and the next you have the variation of v velocity with respect to y, dou v by dou y into dy. So this is what we have. So these are the two equations, additional two equations which we have. So now what we are doing, we need to actually assume, like form a matrix form. So this is like A x is equal to B form. Okay, so this is what we have. So A x is equal to B. So X is a matrix which contains our independent variables, or let's say we have the derivative terms. Okay, so here, so we have dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y. So this is nothing but you have x. Okay, so what is A here? The coefficients actually. So the coefficients of this dou u by. So if you multiply this row with this column, you'll get first equation. You can see it. So A1 into dou u by dou x is the first term. So B1 into dou u by dou y is the second term. So C1 into dou u by dou x is the third term. So D1 into dou u by dou y is the fourth term, is equal to F1. So what we are doing is like we have 4 equations. Those 4 equations we are converting into a matrix form such that all the 4 equations brought together actually. Okay, so if you want to get the solutions, if you want to know the values of dou u by dou x, so these things, so you will just invert this matrix. Okay, so this is about the first equation. For the second equation, similarly you can see. So if you multiply again the second row with this column, you'll get the second equation. Okay, you can verify here. So which is A2 into dou u by dou x and B2 into dou u by dou y, C2 into dou u by dou x, and T2 into dou u by dou y is equal to F2. Okay, so this and all is first equation. So here it is second equation. Here you can see the third equation what we have. Okay, so basically what we have, we again multiply this row into this column. So dx into dou u by dou x, dy into dou u by dou y. So 0 0 0 we have. So next, so we have again 0 0 0. So dx into dou u by dou x and dy into dou u by dou y is equal to du and this. So this equation you will be getting the third one. So this one you will get fourth one. So what we have done, so basically we had rearranged these 4 equations in a matrix form. So this matrix form is like written in the form of coefficient matrix and the independent variable matrix and the source terms. Okay, so in entire CFD, so basically we will, whatever the equations we have, so we will arrange in this form, matrix form, and we'll invert. So basically A is nothing but the coefficient matrix. So X is nothing but your independent variable matrix is equal to B. Okay, so source terms. So this B can be equal to 0, can be not equal to 0, equal to 0. So when you have this not equal to 0 term, so then you have some source term here. So if it is equal to 0, then it is called the homogeneous equation. So this is non-homogeneous, this is homogeneous equation. Okay, so basically here the basic thing is like how do you get dou u by dou x. So in order to get dou u by dou x, so using this Kramer's rule, so let's say, so you have determinant of B divided by determinant of A. Okay, so this is what we need to see. So what is determinant of B and what is determinant of A and how do we find it, we will see. Okay, so the basic thing is, so you know this is A matrix. So A matrix, the determinant is nothing but, so A1, B1, C1, D1 here. So A2, B2, C2, D2. Next dx, dy, 0, 0, 0, 0, dx, dy. So this is the determinant of A. So this is what we have. Okay, so next if you want to get determinant of B, so what we do is like, so it's like I'm just representing, we did actually solve. So what we do is like we will replace this first column of this A matrix with this B here. So for the Kramer's rule, if you want to get dou u by dou x, if you want to get dou u by dou y, so we'll replace this one by second one. If you want to get dou u by dou x, you replace this one by third column. If you want to get dou u by dou y, we'll replace this one fourth column. Okay, so what we have, so let's say the B matrix, let's take this as a matrix. That would be F1, F2, DU, DV, next B1, B2, dy 0. Okay, so C1, C2, 0, dx, same D1, B2, 0, dy. So this is B matrix. So you can see the difference between A and B matrix. So what is the difference we have? So if we want to get this is the Cramer's rule method which we are doing. Okay, so if you want to find the value of dou u by dou x, so what we are doing? So the dou u by dou x term will be always will be there for the Cramer's rule. The first column has to be replaced with the B term. Okay, if you want to get this dou u by dou x. Similarly, if you want to get dou u by dou y, the second column has to be replaced with this B term, B matrix. Okay, so the third column, if you want to get dou v by dou x, so again the B1 has to be replaced with the third one. So again, if you want to get dou v by dou y, so it has to be replaced with the fourth one. So this is what we have. Okay, so let's see. So what we have done. So basic thing is so we have B mat. So if you want to get dou u by dou x, okay, so you should find what is det B and what is det A. Okay, so this is what we have. Fine. So what we are doing? So basically we are replacing the B matrix of the first column, A matrix of the first column with the B matrix. So in order to get this one. So let's say, so B is nothing but so B1 of this will be the first column, and remaining 3 columns will be of A. Okay, so in order to get, so let's say if you want to get dou u by dou y, so what we do? So here A of first column, here B, and A of third column, A of fourth column we have. Okay, so here what we will get? So we'll get dou u by dou y. So same process, like you have to get what is determinant of B and determinant of A. So if you see a determinant of A, if it is equal to 0, so something like it would be some indeterminate structure. So then you will be able to get an equation here. So what is this? So this is the determinant of so basically A, and which is rearranged form. Okay, so using some mathematical operations. So here we are not interested in mathematics. Here we are just seeing so how we can relate this our PDEs actually. Okay, so here we have A1 C2 minus A2 C1. So you have this term, you have this term. So the common thing is you have dy by dx. So before getting du by dx, you should get dy by dx actually. So the meaning is if you want to get u term, so before that u is nothing but dv by, so a velocity, if you want to get you need to get these terms. Okay, so before getting the velocity terms, so you should get so dy by dx, the slope terms actually. Okay, so the curve slope terms you should get. So therefore what happens? So here, so we are replacing this one by A, and this one by B, and this one by C. Okay, so this is what we have. So here you can see clearly that A1 C2 minus A2 C1. So this one is by A. Okay, and next the B term. So this one A1 D2 minus A2 D1 plus B1 C2. So this one is by B, and here you have B1 D2 minus B2 D1. So this is by C. So what we have? So basically the equation what we have is A into dy by dx square so here you have minus, sorry, so we have taken this b as minus of this term, plus dy by dx plus c is equal to 0. So we are written in this equation form. So let's say if you take this dy by dx, so x has some capital K. So K is equal to dy by dx. So what we have, ak square plus bk plus c is equal to 0. So if you want to know, like this is a quadratic equation, so we know basic thing. So if you want to get the value of if you want to get the roots of this equation, so we have the basic formulation. So what is it? So k is equal to minus b plus or minus under root of b square minus 4ac divided by 2a. So this is the basic quadratic equation what we have. So this equation is the basic quadratic equation which we have. So if you want to get the value of, let's say, k using the root method, so if you want to find the roots of this equation, so here you should write this in this form. So minus b plus or minus under root of b square minus 4ac divided by 2. So what is k actually here? K is nothing but dy by dx is equal to minus b plus or minus under root of b square minus 4ac divided by 2a. So this is what we have. Okay. So what we do here, so this is an important aspect. Okay. Again, I'll rewrite here. So what we have, so we have dy by dx, which is nothing but minus b. So again, I'll write here dy by dx. So which is equal to minus b plus or minus under root of b square minus 4ac divided by 2a. So this is what we have. So this determinant is important. So what we have, determinant, let's say this d discriminant, let's say, so b square minus 4ac. Okay, this one we have. So if it is greater than 0, so what happens? You have two real roots. Okay, so if it is greater than 0, so you'll get some value. So let's say you have some 4, like the discriminant as 4, then you'll be 2. So you'll have b value, let's say minus 2. So sorry, like b value minus 4, something like that. So 4 plus or minus 2 by 2a. So let's say you have two roots, in the sense you'll have two equations. So this kind of assumption is for hyperbolic actually. So this will fall into hyperbolic equations. So basically when the discriminant is greater than 0, okay, so then this sort of equation is nothing but the hyperbolic equation. Okay, so during discriminant greater than 0, what happens? So here you will have two equations, because you have plus or minus. So what happens, let's say, so minus b plus under root of b square minus 4ac by 2a. So this would be one equation. So let's say dv1 by dx. So what would be dv by 2? Like this is the second one. So that would be minus b square minus 4ac divided by 2a. So this is what we have. Okay. So here when the discriminant is greater than 0, so you'll have two distinct roots. So you have two equations. So the meaning is like the solution is propagated in between these two distinct curves. This is for hyperbolic equation. So these aspects we'll be seeing in further class. Okay. So what is the other case? So when this discriminant is nothing but b square minus 4ac is equal to 0. So then what happens? So if you substitute, so what happens? dy by dx will be equal to minus b by 2a. So what happens? We have only one root. Okay. So this is what we have. This is for the parabolic equation. Okay. So here for the parabolic equation you have only one curve. So the information propagated. So let's say this is for the sonic conditions if you take for the CFT. Okay. So then after the discriminant less than 0. So what is the meaning? So b square minus 4ac less than 0. So here what happens? We have imaginary curves. So basically you will have, let's say, what is b of plus I some d value by 2a. This is for first equation. So second one would be minus b minus id divided by 2a. So you have these two. So basically this is for the elliptic equation, and here the basic differences what we have is like, so you have first is like hyperbolic, so where discriminant is greater than 0. So parabolic, which is discriminant equal to 0. Then you have elliptic, which is discriminant less than 0. So you have these three things. So here what is happening, where discriminant is greater than 0, so you will have two roots. So you'll get two equations, let's say here. So here one real root. So you have one equation, let's say. So here it is imaginary. So basically here, these two cases, the disturbance or the information is propagated in a confined region actually. So for the hyperbolic and parabolic case. But when the elliptic case, if you see, so let's take an example actually here. So let's say this is some tank. So you have water here. So in this water, like if you throw some stone, what happens? The disturbance is propagated equally in all directions to all boundaries. So this type of scenario will come into this elliptic case. Okay, so basically the elliptic equation. So what we are discussing is for the boundary value problem. So basic example of elliptic equation what we have is like, let's say, so dou square u by dou x square plus dou square u by dou y square, let's say, is equal to 0. So that this is the one form of elliptic equation. So there is no time dependent term actually. Okay, so here what we have, like for the elliptic equation, the boundary or the information is propagated in all directions to the all boundaries, and here it is not like you don't have any time information term. Okay, it is not marching solution. So parabolic and hyperbolic, so these are the marching solutions. And here you have two real, like for the hyperbolic you have two real roots. The meaning is like the disturbance is confined to certain region and is propagated in between these two curves. Okay, and if for the parabolic case, like let's say the solution, let's say this is marching like this with respect to different time levels. So if you take this as t and x, so time t is equal to 1, 2, 3, 4. So like this, the solution is propagated. So basically this is like initial value problem. Like with the initial conditions, the solution is progressing with respect to time. So basically here the elliptic equation. So even what you say, like steady problems actually. So these are like coming under the steady case. So these two are coming under the transient case. Okay. So in the next session we'll be seeing clearly. So what is second order? How do we discriminate? Like how do we see a basic second order PDE, and how do we classify the second order PDE with respect to hyperbolic, elliptic, and parabolic equation, and how do we relate these equations to our continuity momentum equation? So we will see actually. Why? Because in our Navier-Stokes equation, so you have these terms. So basically, you have dou u by dou t plus u into dou u by dou x plus v into dou u by dou y is equal to minus 1 by rho dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square. Okay, so let's say this is then basic form of basic 2D x momentum equation. So here this time. So here the derivative, whatever you have, like this thing is non-linear form. So you have time derivative term. So if this is 0, what happens? So you have, if this is 0, so you have like u dou u by dou t, and here you have this thing. Okay, so here you can see this is like elliptic form, and here you can see this is some hyperbolic form. So the main Navier-Stokes equation or X momentum equation, so will fall into this PDEs actually. So if you just use some assumptions, and if you synthesize this equation, then you will be falling into some other form. So that's why we are learning this classification of PDE. So now in the next classes, like for the next modules, so we will first see how a second order linear PD or second order PDE is classified with respect to these aspects: hyperbolic, parabolic, and elliptic. And then after, how we relate for our Navier-Stokes equation, we will be seeing in the next module. Okay.
Like, share, and subscribe. Hit the bell icon for more updates.